Alhamdulillah. So over here, we have 45.09 times to the power of 4. I move 1, 2. 2 times to the left. So I will add 2 to my exponent. And my answer will be 0.4509 times to the power of 6 after I plus with 2. So this is the normalized form. So you need to remember the rules. I guess these all mathematics. Just a mathematic which you already learned it from your primary school. And then on the Reddit point, of course, it is at your secondary school. So it is more on mathematics. So don't excuse like COE subject is very hard. But basically it is more on mathematics for this point. So suppose it's going to be easy because we already do it several times since we are in primary school. So over here, we have the example of decimal and binary. Let's take a look one by one so that you're going to be more understand on that. So I have 743.09. I will make it 0 point something. So I can see over here, I'm going to move to the left. 1, 2, 3. When I move to the left 3 times, left, I'm going to add. So I'm going to add 3. My answer will be 0.74309 times 10 to the power of 64 after I add 3. Easy, right? So we have another example on binary. Over here, wait, I have a meeting. I need to see first. What is this? Untuk status apa? Hadir. Okay, sorry. Okay, here we have another example. You can see 10.0111. Okay, this is of course your binary. It's mentioned over here 2, which is your base 2. So you have times to 2 the power of negative 110010. Apa ni? What is this? So you can just change into the decimal using your scientific calculator. So over here, how are you going to make it How you going to make it normalized form? So you going to make it 0 point something, right? So if you look into this one, you're going to move like 1, 2, and you put somewhere here, and in front there is 0. So how many times you move? You move 2 times. So you're going to add 2. Sorry, okay. Going to add 2 here at your exponent. So if this is in binary, you're going to change 2 with the binary. Don't just simply times 2 over here. It's totally different. So please make sure this one is binary or decimal. If it's binary, you're going to plus with your binary. 2 in decimal. Ya Allah. 2 in decimal is similar to 010 in binary. So you just add and later on you will get this answer. So easy. Now we have another third example, which is over here. It gives you the decimal value for your exponent. You can represent your exponent for your binary form in terms of decimal and also binary. Both can. See, you can. So over here, this is the number. Where to move? I'm going to get 0 point something. So if I look into this numbering, I will move to the right. 1, 2, 3. Oh, oops, until 3. So I'm going to put my radix point here. Then I will get 0.11 blah 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 blah. And how many times? 1, 2, 3. 3 times to the right. 3 times to the right. Then I'm going to minus 3 because I'm going to the right. Check back your rules. To the right, you're going to subtract. To the left, going to add. Easy, right? Just remember that. Then you can easily get the answer. So this is not the big problem for you. Now we're going to move to a simple model. So over here, this is the normalized form for your floating point number. You have 0 point fraction, base, and exponent similar to what we look into all the example that we already go through. So this is the general form or the standard. Aja standard pun salah. Standard. So this is the standard of the normalized form for your floating point numbering system. In binary form, you're going to have sign bit and then exponent, sign bit, and significant. So it's already changed its place. This one is a simple model. For your plotting number consists of 3 parts, which is sign bit, exponent, and then your significance. So what happened? What is this one? This one is the standard when you need to change the form of your normalization. You're going to change it into binary form. In your binary form, it's going to totally change the place. I give you simple example. Simple example. Let's say you have 0.1. We just use 1 so that it's going to be simple. Times let's say your base is 2 because it's a binary, and your exponent, let's say, is going to be positive 0, 0, 1. Because we just want, it's a simplest example I can give. So in terms of binary form, how you convert it? So in binary form, if you have this number, you're going to change it into first your sign, your bit sign, whether it is a 0 or 1, depend on your sign bit, right? If it is positive, what is the sign bit? If negative, what is the sign bit? We already learned it. And exponent. Over here, my exponent, let's say 0, 0, 1. My bit over here, let's say it is positive 0. And sign bit again, let's say it is 0. I forgot why it is 1 bit. It's okay, we try to do it. And our significant, we have 1. So is there any example? Okay, so you're going to get like this, how you're going to convert from your normalized to your binary form. So we're going to look into the example. So over here, these two sign bit are not good for sign, as it is extra cost. So need new representation. It's okay. So that's why I mentioned over here it will be a problem. It's okay. We're going to look into it. So the point is your exponent and your fraction will be twist in place. You can see over here. This will be on the left. Your fraction will be on your right after this. When you have your general form, when you want to convert it to the binary form, you're going to put like this. So we look into the example. Example, you have 14 bits of model for floating point format. It's already give you 14. So you're going to see you have 14 bits, and you're going to calculate. You have 8 bit for your fractions, and 5 bit you have already have 13, and including sign, which is 1 bit, altogether you're going to get 14 bits. So this one is just example for 14 bits, but the next few example exercise will be using our IEEE 754 floating point standard. So the standard will be different because this one is 14 bit. The standard will be in, where is it? You're going to do in 32 bits and also 16.4. 32 and 64. But later on we will look into it. Here first, we're going to look at example number 17. Okay, let's say we have unnormalized binary. This is our numbering. Let's say store the decimal number. So this one is our decimal. 17, you change it into binary. You're going to get 10001. If you not understand, please try to do your calculator or you convert it one by one. This one will be 1, 2, 4, 8, 16. So 16 plus 1, you will get 17 in decimal. So from here, you're going to do the normalization. Your normalization, you will do 0 point something, right? So this one, your numbering, you are to the power of 0. Then, you're going to normalize it. You will get from this radix point 1, 2, 3, 4, 5. Your radic point will be here. Then you will get like this. Kalau to the left, if it is to the left, it's going to plus 1, 2, 3, 4, 5. 5 to the power of 5. So you get this. After you already normalize it, this one I already normalized 0.10001 times to the power of 5. This one, decimal. Where we want to convert to binary form, we need to convert it first, which is it going to be 0, 1, 0, 1. 1, 2, 4, 8. So 4 plus 1 is going to be 5. So in 14 bits, what you going to have? You're going to have your sign. You are positive number. Positive will be 0. And if you still remember, you have 1 bit or 5 bit and 8 bit. 5 bit for your exponent. Your exponent will be 1010. But this one I just put 4. You need 5. So you need to add another 00101. This one is sign bit. This one is exponent. I made the separator or another one. So I have the significant of fractions. So this is the one I need to put 10001. But over here there is another rules. If you are taking the exponent number over here, you add the 0 in front, right? Tengok. See over here, I put in front. 5 in decimal, it's suppose 101. I add 0 in front to complete it to be 5 bit. Let's say example, I have 2 to the power of 2. So 2 over here in binary is going to be 10. If 10, I supposed to add another 30 in front. So the first rule, if it is exponent, it's always padding to the left. So you're going to add 0 in front. While for my fraction number, this is my fraction number, I have 10001. Fraction is always padding to the right. Then I will add another bit, which is to complete add bit. This one is only 5. I add another 3 to my right, and then this one to my left. Is it clear? So this is the rules for 14 bits of binary form. Is there an example? Okay, there is another example, but it's too big. Write the decimal number 65536. Okay, I'm going to pick lucky person to convert it into binary. Salvar Ahmed, you didn't turn on your webcam. Please convert the where is it? Please convert the 65536 to your binary. To binary, not floating point. Salvar Ahmed, where are you? Are you there? Salvar Ahmed?
Hello?
Yes. What is the answer? You don't know the question. Sabar Ahmad,
Yes, ma'am.
what is the answer?
Sorry to say I didn't notice because I am doing two classes at the same time.
Why you do this two class in
Because
one time?
I got on this class at the same time only one as journalism.
You cannot have two class in one time. Then you're going to
I'm trying
have
to skip it. I'm trying to skip it.
no. You cannot. You cannot choose because both is important. What you need to do is you need to go to the academic office and inform that you have clash timetable. You cannot choose one which is important, one is which is not important, because both subject is important. Doesn't
Exactly.
matter what subjects are. Is it
Actually,
okay?
that time, yeah, the lecturer was talking about the assignment. I was focusing on that.
So
Sorry for
next
that.
class next week, you cannot have this.
Yeah, yeah, sure, sure, sure.
I want you to pick which one is the class. Maybe you need to change your timetable. You need to fix it with the academic office. Is it okay?
Okay, ma'am. Okay, okay.
Okay, Nafi Ahmad. Nafi Ahmad.
Yes, doctor.
What is the answer?
It's too big to store it in the 14-bit model, right?
No, I just want you to convert. I want you to convert 65536 to binary, because I don't have scientific calculator and I'm too lazy to type on my Google.
Uh,
So, mm.
no, it exceeds the capacity of it.
Is it? Huh?
It exceeds the capacity. It's too big.
Oh, it's not that, even 64 also.
Yeah.
Mm.
I think it's the limitation of this model.
Sure. Is it sure it's to be?
2 to the power of 16.
Okay. So it will be 100000 something like that, right?
Yes, until 16-bit or 15-bit.
16. Wait. Yes. You can also see my screen, right?
Yeah, we can see.
Okay. I just convert it into binary using the Google software. So where should I start? Okay. Okay. I have one 0000. How many? 16. Ah, I forgot.
Yeah, 16, I think.
1.0 times 2 the power of 16. If I'm not mistaken, isn't it? 16, right? So, uh, how you're going to do is you're going to write like this 1 until 16 time of 0. Then you need to normalize it. How you going to normalize it? You're going to move until over here 0.1. So 0.1, suppose you're going to move how many time? Is it 15? 15 time or 17 time? Maybe you can calculate it. I'm so lazy to do it now. So please calculate it. Okay, just assume it will be 0.1 and you move it 15 times to the left. So you're going to get to the power of Add, kan? Right. So 15, isn't it? So we just assume, okay, you need to calculate by your own how many times it will move to until you get 0.1. And the rest will be 0, 0, 0, isn't it? So what you're going to see first, this is positive number. You're going to put 0 over here. And your floating, your exponent, let's say it is 15. So 15, Alhamdulillah. 1, 2, 4, 8, 16. So I'm going to have like this. So this is my 15 in binary. So I'm going to write 0.
That's 13, not 15.
12 plus 13. Okay. It's going to be 1 over here, isn't it?
111, yes.
Okay. Thank you for correcting me. Okay. What rules you need to put is because this one is 5-bit. You need to add 0 in front. So you already correct for both. Now for the point of your fraction, because you have too many, until then you just put it 0, 1, 1, 1, something like this. Okay, so this is not the correct answer. You need to do it by yourself, which is how many point you move to the left. So I just give you the overview how basically this is working to you to do the normalized process and to convert it in the binary form. Okay. So now we move again to another subtopic under by exponent. So this is used unless the R triple E standard is mentioned, then all the method, others method going to use the bias exponent methods. So it's already mentioned. This method will be used unless in your question is stated you need to use IEEE standard. If it's not mentioned in the question, you're going to use Bias exponent method. So one obvious problem with the method model is negative exponent cannot be representations. See, you cannot represent the, if let's say you have 0.1 times to the power of -5. I just give you example. So you cannot represent it. So there is a problem. The solution. So what is the solution is you're going to use the bias exponent. So previously this method will be having the problem or error when you have negative on your exponent. So the solution, you will use the bias exponent. For negative exponent only, okay? The problem will be on the negative exponent. So what you're going to see is you're going to have the form of sign similar, which is positive or negative, by 6 exponent. So previously you just use exponent. Now you're going to use the bias exponent, which is called as EB. And this one is similar, which is your fractions. So where your EB is a bias exponent, N is the bit of your exponent format. Bias value is B to the power of N minus 1 normalized exponent E. Okay, this is all the equation that you need to memorize. So this is equation. Of course, equation we need to memorize it. Then after we memorize, we need to understand how we're going to apply and implement it into the question. So over here, the bias value, the number near to the middle of the range of the possible value that we select to represent 0. So typically the bias value B is equal to the, okay, this one is already mentioned at previous pages, where n is the number of bits in the binary exponent. So positive value, any number larger than 2 the power of n minus 1 in the exponent field, bias plus exponent. While for negative value, any number less than 2 the power of n is exponent field is a bias value minus exponent. You read this, you're going to feel like, oh, apa benda ni? What is this? So let's take a look example, then you can understand more. You need to follow the step. First step, you're going to change to binary any decimal number, but you are lucky if the number is directly given with the binary. Second, do the normalized number. If it's already normalized, then bonus for you. No need to do step 1 and step 2. Third, change the number to bias exponent. This one you need to learn how to change the number to bias exponent. And fourth is form the floating point format 3 field. This one you need to check what is this. So let's say there is example number 18, return to example for 17, which is on 17 decimal. So similar example, if you look into, you have this example number 17. You will get this kind of answer because this one is positive exponent. Now, if let's say over here, you need to calculate the bias value. So B is to the power of n minus 1. This is your n. N minus 1, 5 minus 1. You will get to the power of 4, you will get 16. This is the value of your bias. B equal to the power of n minus 1. This equation already stated here. N is your exponent. See? So you know n, then you will get B. So that is 1. Next, after that, you need to calculate the biases exponent, which is EB. With the equation given, E prime plus B. Look back your equation over here. Bias exponent. So bias exponent, you will get EB equal to E prime plus B. Then you get E prime plus B. Your E prime will be 5. Supposedly it's mentioned over here. But it's not mentioned here, your E prime. And you plus with your 16, your B over here. So your E from here, same to basically is like your N. So you will get 21. Then you already get your answer. Sign, bias exponent, and then this one is your fraction is similar. So bias exponent is 21. If it is 21, it will be 1, 2, 4, 8, 16, 1, 0, 1. Okay. Correct. See, you can just use your scientific calculator. It's very easy. Just press and you get answer. Okay. 21 decimal. You get binary 10101. Then you will put in Ising exponent. Your fraction will be similar. No need to change anything. So this is the form of like this. The difference will be at here only. Okay, so you need to memorize this equation and this equation. But for the normalized exponent, you're going to use this one. But we are currently using the biases exponent. Why? So over here, biases exponent is equal to the power of n, where n is the number of bit in the binary exponent. So it already mentioned what is n. Number of bit in the binary exponent. And if it is positive value, and any number you're going to plus. But if negative value, you're going to minus. That's why we are doing like this, because we are positive value. So easy, right? We just convert it into the biases exponent. So example number, okay, we have another example. Let's say store decimal number 0.25 in the floating point. This one is the floating number. How you going to convert it? Please look back the video for numbering system. There is a conversion how you convert decimal to binary, binary to decimal. But there is two different way. If you are using the integer number, it's easy for you to direct convert. When you are using the floating number, this is the way how you're going to convert from decimal to binary. Okay, so if you still don't know, please look the video I share already in the e-learning. Okay, you have 0.2. How are you going to convert? You're going to do repetition multiplication. This is the standard. This is not the one I created. This is the standard. If you want to convert decimal to binary, for floating point, you're going to use repetition multiplication. So 0.2 you times with 2. You will get 0.5. 0.5 you bring over here. Times 2 you will get 1.0. So, sorry. Okay. So, after that you're going to get 25 decimal. After you get 10, you will get 0 point. Your floating point will be from up to down. So you will put 0, 1. I'm not going to focus in this class how you're going to use this repetition multiplication. This one you already learned in your digital logic subject. And this is a mathematical terms. I already share you the video. Please take a look back and you will see. Okay, this is easy for you to just convert it. So after you get this value 0.01 times to the power of 0. This is the value. Okay, then you need to change it into normalized, right? Okay, you're going to move it like this. So one time only you will get 0.1 times to the power of -1. Oh, I'm afraid this is a negative number. How I'm going to do? So over here, if it is a normal form, it's you're not going to uh change it directly because it's a negative. So this one is positive, going to be 0, and this one is will be -1. I want to just let go this first. I just want to put it this one. So I have 0, 0, 0, 0, 0, 0. Then this one you need to be putting here. You need to, I forgot the equation basically, so that's why. Um, okay, this we already done. Normalize the binary. Okay, my answer is correct. Then you need to apply the equation. This one, the equation first. You need to get the b to the power of n minus 1. Why the n is 5 over here? This one, previously I'm wrong. I think n is the digit. Where is it? Okay. N is the number of bit in the binary exponent. So your exponent will be 5. 5 bit. Where is your 5 bit? This is the bits of your exponent. That's why it will be 5. So sorry for the example over here. I show you this 5 is from your north. This one is your E prime. This is your E prime. And 5 over here is depending on your bit. See, I also forgot. And is your bit of your binary exponent. How many? It is 5. Mana? Where is it? Okay. N bit. This is N bit. You going to have 5 bit for your bias exponent. So that's why you will get this 5. B equal to the power n minus 1. N is your bit. And then after that, you will get 2 to the power of 5 and 4. You will get 16. Then, how are you going to get EB? EB equal to 16. I forgot the equation. Refer back to the equation. EB equal to E prime minus B. Why I pick minus? This one. If negative value, you're going to minus. Okay. Go back to the equation. Question. I have B equal to 16 and my EB equal to E prime minus my minus apa? I forgot again. Minus my exponent. So my exponent, what is the bias value minus exponent? So my exponent will be my exponent lah. This is my exponent. So my exponent will be minus 1. Because this one is minus, it's already minus. So it will reduce. So the bias exponent will be 16 minus 1, it will be 15. So this 15, you need to convert it into binary. So for your binary, 15, you will get Tadi I salah kan? 1111. So that's why you will come up to this. You put extra 0 over here, and this one, you just put it here, you add another 0. So it's easy, right? So please try to do exercise 0.8. How you get your answer. And another exercise is 2.9. So I already give you three example. Now you're going to do 3 exercise by yourself. So, is there any question until here? Because I'm going to move to next subtopic. So, any question? Easy, right? So, I hope that all of you will score in your test 1. So, most of you will be getting 80% above. So, let we move to next subtopic. Okay, we have IEEE 754 floating point standard. So in this, that is why previously, if you still remember, I mentioned about 32 and 44, 64 bits. So 32 is single precision. 64 is double precision. Okay, floating point, computer arithmetic that represent number which is binary point is not fixed. So you have this kind of format. A standard scientific notification for real normalized form. So it's going to be different. The form, general form is a 1, and then there is a s, which is the sign, fraction, and then you have times to the power of your exponent value. So let's take a look the example for your 32 bits single precision. This is your floating point number. You have 32 bits, 0 until 22. 23 bits is only on your fraction. Add bit for your exponent and extra 1 bit for your sign. Where? Okay. The size of exponent and fraction give MIPS computer arithmetic extraordinary range. So the smallest fraction is this one. The largest number is this one. So this is called as single precision, which is one word. In your digital logic, you already look into how many bits have available in 1 byte, and then you also look into words and etc. So please look back what is the words, how many bits. Now you know one word is equal to. So one word is equal to 32 bits. It's called as single precision. So the size of exponent, okay, we take a look into. Unfortunately, single precision floating point still possible for number to be too large. So overflow, the exponent is too large. Underflow if the negative exponent is too large. So that's why, although you have, maybe this is the one that your friend created. This is the method that your friend created. And because you see, there is a lag, there is a niche, still there is a niche or gap. So you improve with a solution. So the solution is using double precision floating point. So over here, you can see that copyright. Double precision, you have words on 36 bits. 2 words. How many bits you have? This one is 32 bits for one or single precisions. For double precision, you have 32 bits. So you have another 32 continuously. Continuous. So you have fractions, another 32 bits. So the in front is all similar. So the smallest fraction will be this one, this number, and the largest will be these numbers. So this is on the single precision theory, what you need to know, and also the double precisions, what you need to know, especially in terms of the formatting. Next, we're going to move on the floating point standard on the representations. So over here, you can see that this standard has greatly improved. But you can read this. I hate reading basically. So the most important is the significance, which is 1 plus the fraction. So single precision 24 bits, double precision you have 53 bits. 0 has no leading 1. What is all this meaning? Later on we will see on our example. So the representation. Uh, Wait, where is my? Uh, I need to charge. Aduh. Okay. The representation of normalized floating point in IEEE standard. So you have this form -1 as what is as it is a sign, plus, which is positive, is 0, minus negative, it will be 1. Is 1, of course you already know. And normalized exponent is E prime. So this is E prime for normalized. How you going to see normalized and unnormalized? Totally different. Why I said it's different? IEEE standard normalized is 1 point something. While previously you check the floating point standard, not the IEEE, the standard is 0, point something, isn't it? So now please change and refresh, clean your minds. We are going to look into IEEE 754. So don't be confused. Different people. Okay, this one is created by you. Another standard are creating by your friends. So yeah, different kind of people, different thinking. So that's why in IEEE they have their own standard and normalized standard. So this normalized standard is there is only one single non-zero before the radix point. So before the radix point on non-zero. But for previously you learned normalized is after your radix point, right? So say there is a difference. So now please change. And the question, if you basically in the question is going to mention carefully whether it is a triple E standard or what standard. So over here, this is the normalized for the IEEE 754 standard. This is normalized, this is normalized, this is unnormalized. See, last time you see this is normalized standard. Now it's going to be unnormalized. So complete the table to make it normalized using a single precision floating point. So over here you can just move it until it's to be here, and this is already normalized, but this one you're going to move until here. And how it's going to be normalized, please try to do it. And what is the exponent? So over here you will see the exponent or E prime is already stated there. So let's say I give you example like this. This is very easy. I just copy and paste. 0, 0, 1. You do the rest. This one, your E prime is 0. So you try to do A, B, and D. I'm very clever because I pick the easiest exercise. So that is on the normalization under IEEE 754. Please check back. If you go back to the previous normalization, where is it? Okay, you can see that normalized process. The normalized thing is after 0 point, which is after your radix point, then it's going to be normalized, right? Like this. This one is unnormalized. But now when you are this one is under floating point. Normal floating point representation, but when you come into the IEEE normalization, it's going to be different. So I just want you to see why this lecturer sometimes it's saying this is normalized. Then now it said this is normalized. So this is not my wrong. I just fish. But this is the people who did these methods are wrong, because maybe if I'm the one that created, maybe I will just make it similar to all. But yeah, of course, different method, there is a different reason why the peoples or the one that created the standards creating just that way. So you just need to follow. If you want, maybe you said why you want to learn all of this. So if you said like that, maybe you can create your own standard. Maybe you will come out with new standard IEEE 2021. Who creating this standard? Your name. So people will say, why I need to learn this standard? then that come out, you give your own reason why you correct that. So over here, we will move to by notation. So by notation, see there is we are until we are still under IEEE 754. So placing the exponent before the fraction simplifies sorting of the floating number, blah blah blah. So you can read it. I think on the sentences you can just read. But in the example, I will try to explain until you understand. So, however, using second complement in the exponent field make a negative exponent look like it is a big number. So, if let's say you have this -1, -1 is sometimes it mentions like this decimal, or maybe you have -2. So -2 in decimal it will be 10. So if let's say you want to change it using second complements, you already know that it's going to be 10, 10, 1, and that 1011. Then you're going to add 1, then 1, 1, 1. So you can see over here, instead you have only -2 as your exponent, and using the binary you will get -1, minus 0, 0, 1, 0. This is minus. Because of last time you already learned, when you have minus, you're going to have problem. So you learn second complement. But when you change it into second complement, of course, you're going to remove this. It's going to be to the power of 1110. See, it's look big. So that's only the point I want to explain on the sentence. So it's look like a big number. So that will be a problem in your exponent later on. See, you just change it into your exponent, so it's showing that it's very big in number. Then you have the bias value. So that's why you're going to have the bias value. So this is the equation, -1 s times 1 plus fraction times 2 the power of EB. Uh-oh, I got another meeting. Okay, I try to speed up. Uh, one meeting already finished. Coming up next meeting. Basically, why I have meeting on this time. We lecture from Perdana, which is from UTM. They will follow our timetable. So basically, today I'm going to be free from 2 until 5. I will be free, but I was assigned to help the MJIT due to the lecturer move to different IPTA, right? So that's why my timetable is already occupied with different subject. So over here you can see there is example. You're going to change into the biasing standard. If you compare to the normal standard, where is it? Okay, this is your normal standard. Oh, this one is a normal floating point in IEEE. And when you are using the biasing, this one will change to bias value. They start already. Uh, okay. So over here you have 1.5 0.0, this is binary, of course, to the power of -1. So -1, your exponent will be -1 plus your Bising. So Bis value, what is the value of Bising? To the power of n -1 -1. This is fixed for single precision. This is fixed for double precision. So no need for you to head it to memorize this equation. You're going to have fixed number for the same single precision and double precisions. So if you are dealing with the single precision, which is 32 byte, it is will be look like this. -1, this is from here, and you will come out with this value. You just convert it into the binary. So this is the example, you see. So maybe you can try to look into this also. This is under 32 byte, and this one is 64 byte. So please try to do the exercise number 2.12. And I cannot cover. My prof is already in the waiting for me. Okay. So I need to finish it now. And all of this until the end of this chapter 2, I already uploaded into your e-learning. So if you look on the e-learning, all I already upload. So please try to play the video and please try to understand and do the exercise. And next week, maybe I just do the Q&A session for the rest, and I explain the important part only. And we will jump directly to our module 3 and start our lab 1 because we going to do similar and parallel test 1 with the rest of other section, which is normally now they already go through until module 3, and yeah, some of that's already module 4. So we are backdated, right? Due to last time we start at week 3. So we need to speed up. Is it okay? So please make sure you go and check it back, the video I provided. Today class also I will share in your e-learning later on. Try to do your lab 1 also after this. So here, for those who still did not scan the attendance, you can scan your attendance while it's already 37.
Ma'am, I have a question.
Okay.
Request actually. Can you share the slides in PowerPoint format?
Cannot. This one is only for lecturer. PPT, right?
Yeah, because we cannot show some answers because we want to make sure.
In the slide, I think all is similar with your notes. Is it different?
Yes, because in
Yeah.
PowerPoint you can show.
Important point. It has some missing terms in it, like
Yes,
that.
and
Just
a lot
given the
of
Oh.
them.
I need to check with other lecturer, but because if I just change it into PPT, PDF, let me try desktop. Oh, I want to change it in PDF. Okay. Okay, let's take a look. Oh, this one is after I conteng. I did something. Code, right? maybe. Hmm. Okay. If you request that, I need to ask others lecturer because this one is supposedly lecturer version only. Maybe there is also why they limited that for student and so on. Okay. So any other question?
Yes,
When is the
doctor.
test?
Yeah.
When is the test?
I already share. It is 24, isn't it? I forgot the date. I will re-share to your WhatsApp group this month. Another about 1 weeks to go. Not even 2 weeks. I think 10 days.
What's the form of the test, ma'am?
It's going to be multiple choice, and there is two part A and part B. Part A will be a multiple choice, and part B you need to answer it. Uh, Subjective.
So we will do it in the e-learning then.
Yes, in the e-learning. All the answer will be in the e-learning. You need to upload it into the e-learning
Okay.
directly.
Online or offline?
Online or offline? Online, of course, we're going to do parallel session with other section.
Okay.
Doctor, it's modules 1 and 2, right? Only 1 and 2.
Yes, model 1 and 2.
And it's
Okay.
only 10%, right?
I forgot about the percent, but I will check later on the CI. Later on before the test, normally I will do mock test normally with my student. So that's why we need to speed up a little bit. Okay.
Ma'am, the
Ma'am,
QR code.
can you give us some exercise before the test so we can do better results?
As I mentioned, I'm going to do mock test. Mock test means that we're going to do exercise together. The mock test normally is look like similar to your test, so you will see the format exactly on similar to your test. Okay.
Can you share past year test,
What again?
previous
Past-
year test
Okay,
table?
I will share it in the e-learning later on. Okay.
Okay, thank you.
Okay. But please be aware that last time it's all physical tests, not online test, right? So maybe there might be slightly different.
Okay.
So any other question? So if there is no question, you can scan the Q. I think why it's already 37. Hmm, nak berbuka. Okay, I need to go now. It's already wait for me. Thank you. Bye
Ma'am,
bye.
the QR code.
What again?
Thank you, doctor.
Okay. Thank you. Bye bye.
Ma'am, I haven't scanned it.
Okay, please do now. Hurry up. Raise it.
Wait. Okay, enter. Okay, thank you, ma'am.
Okay, see you, man.
I don't know why I'm getting error when I want to run the code, the templates.
Can you WhatsApp me and we try to do personal session later on? You are mute.